Niels Henrik Abel's Recherches sur les fonctions elliptiques, published in 1826, stands as a monumental achievement in the history of mathematics, fundamentally reshaping the landscape of complex analysis and laying the groundwork for numerous subsequent developments. This essay delves into the intricacies of Abel's work, exploring its genesis, core concepts, immediate impact, later evolutions, critical reception and enduring the intellectual climate preceding Abel's contributions teemed with activity surrounding elliptic integrals. These integrals, arising naturally in problems such as calculating the arc length of an ellipse, which is where they obtain their name, or the period of a pendulum, presented formidable challenges to mathematicians of the time. Legendre, a prominent figure in the field, dedicated a significant portion of his career to their study, amassing a vast collection of results and establishing a system of classification. However, Legendre's approach remained largely descriptive. A deeper, unifying theory remained elusive. Abel's genius lay in his bold inversion of perspective. Previous investigators, including Legendre, focused on the elliptic integral itself, viewing it as a function of its upper limit of integration. Abel, in a stroke of profound insight, considered the inverse function, effectively treating the upper limit of integration as a function of the integral's value. The seemingly simple shift in viewpoint unlocked a treasure trove of previously hidden structure and revealed a far richer theory, a perspective that, one might say, held the keys to the mathematical kingdom. To elaborate, consider an elliptic integral of the first kind, expressible in general form as the integral from 0 to x of dt divided by the square root of the polynomial a 0 plus a 1 times t plus a 2 times t squared plus a 3 times t cubed plus a 4 times t to the fourth power, where a 0, a 1, a 2, a 3, and a 4 are constants. Legendre and others studied the properties of this integral as a function of x. Abel, conversely, defined a function, which we may denote phi of u, such that u is equal to the integral from 0 to phi of u of dt divided by the square root of the polynomial a 0 plus a 1 times t plus a 2 times t squared plus a 3 times t cubed plus a 4 times t to the fourth power. In other words, phi of u represent the value of x that makes the elliptic integral equal to. This inversion proved to be remarkably fruitful. Abel demonstrated that these inverse functions, which he termed elliptic functions, exhibit a property of double periodicity, a characteristic absent in the elementary trigonometric functions. Specifically, there exist two complex numbers, omega-1 and omega-2, with a ratio of omega-1 to omega-2 not a real number, such that phi of u plus omega-1 equals phi of u and phi of u plus omega-2 equals phi of u for all u. This double periodicity constitutes a defining feature of elliptic functions, setting them apart from their single periodic trigonometric cousins. Furthermore, Abel established addition theorems for these elliptic functions. These theorems, analogous to the trigonometric identities for the sine and cosine of a sum, provide explicit formulas for expressing phi of u plus v in terms of phi of u, phi of v, and their derivatives. The discovery of these addition theorems represented a significant breakthrough, facilitating the manipulation and analysis of elliptic functions in a manner previously unattainable. The immediate impact of Abel's Recherches was limited, due in part to its delayed publication and the prevailing mathematical climate. Legendre, although deeply impressed by Abel's work, struggled to fully grasp its implications, clinging to his established framework. However, the seeds of a revolution had been sown. Abel's ideas began to germinate in the minds of other mathematicians. Over the ensuing decades, Abel's elliptic functions gained widespread recognition and became a central topic of research. Jacobi, another brilliant mathematician, independently developed a similar theory of elliptic functions, leading to a period of intense competition and cross-fertilization between the two. Jacobi's work, characterized by its computational prowess and focus on concrete applications, complemented Abel's more abstract and conceptual approach. This friendly rivalry propelled the field forward at an accelerated pace. The theory of elliptic functions experienced a profound generalization in the hands of Riemann. Riemann introduced the concept of a Riemann surface, a geometric object that provides a natural domain for multi-valued functions such as the square root or the logarithm. He demonstrated that elliptic functions can be viewed as meromorphic functions on the torus, a surface topologically equivalent to a donut. This geometric perspective not only deepened the understanding of elliptic functions, but also paved the way for the study of more general algebraic functions and their associated Riemann surfaces. This was, in effect, a marriage of analysis and topology with profound consequence. The influence of Abel's work extends far beyond the realm of pure mathematics. Elliptic functions find applications in diverse areas such as physics, engineering, and cryptography. For example, they arise in the study of the motion of a pendulum, the propagation of light in nonlinear media, and the design of secure communication systems. Elliptic curve cryptography, in particular, leverages the algebraic properties of elliptic curves, closely related to elliptic functions, to provide robust encryption algorithms. Abel's Recherches was not entirely without its critics. Some mathematicians found his arguments to be overly concise or lacking in rigor, a common criticism levelled against many pioneering works. However, the power and elegance of his results ultimately silenced the skeptics. Modern treatments of elliptic functions often employ more sophisticated tools and techniques. Abel's original insights remain at the heart of Abel's work directly influenced Carl Weierstrass, whose approach to elliptic functions was deeply rooted in power series expansions. Weierstrass rigorously established the analytic properties of elliptic functions, building upon Abel's foundational work. His work, in turn, influenced a generation of mathematicians, solidifying the position of elliptic functions as a cornerstone of complex analysis. Conversely, Abel drew inspiration from earlier mathematicians, most notably Euler and Gauss. Euler's work on the arithmetic geometric mean, a process for computing the common limit of two iteratively defined sequences, provided a crucial stepping stone towards the understanding of elliptic integrals. Gauss, although he published little on the subject, made significant unpublished discoveries related to elliptic functions, some of which anticipated Abel's results. The extent of Gauss' influence on Abel remains a subject of scholarly debate, but there is no question that Abel was aware of and deeply admired Gauss' work. It represents a fascinating case study on simultaneous discovery in mathematics. In conclusion, Niels Henrik Abel's Recherches sur les fonctions elliptiques represents a watershed moment in the history of mathematics. His innovative inversion of perspective, coupled with his discovering of double periodicity and addition theorems, transformed the study of elliptic integrals into a vibrant and fertile field. Abel's work continues to inspire mathematicians and scientists today, a testament to the enduring power of his insight and the profound beauty of his mathematics. His comparatively short career, tragically cut short at the age of 26, yielded a body of work that secured his place among the giants of mathematical history, proving that profound contributions need not always stem from decades of labour. Indeed, sometimes a single, brilliant flash of insight can illuminate an entire landscape,